Welcome to another exciting night of related rates. So I just called this related rates 2. Tonight we are going to focus on the shape of a cone. Yesterday we hit the triangles. Today's all about the cone. So hopefully you can recognize a cone. Obviously your cone could look this way. And I just want to clarify we have a radius in a cone and a height. And these cones are perpendicular, so they do make right angles. Our cone could also obviously be inverted and face upside down here. And I could have, again, my radius and my height labeled. Now there's something special about cones. Cones are always going to have a ratio, and you're going to hear me talk about this in every single problem. Our ratio is always radius over height. Okay, and that's key in solving all of these problems. Radius over height. So, question 1, we have a paper cup which is in the shape of a right circular cone. So let's stop there and draw it out. Picture this cup shaped like a cone. Okay, maybe you're thinking like a snow cone type thing. So it's in the shape of a right circular cone. And that right circular cone is telling me that my height, of course, is perpendicular. And it creates this nice right angle. It is 16 centimeters deep. Okay, so that represents my height, 16 centimeters. And has a radius of 4 centimeters. Water is poured into the cup at a constant rate of 2 centimeters cubed per second. All right, so two things to catch. They use the word rate, so we know that's a derivative. Now, if I'm filling this cup up, what am I describing about the cup? If I'm filling it up, give me a word from geometry. We're talking about its volume. And what should have given it away also is that the units say units cubed. So I know the derivative of volume, or dV dt, is equal to 2 centimeters cubed per second. So again, I've got that two ways from common sense telling me if I'm filling this up, I have volume, and those units, cubic centimeters, represent volume as well. Now, since this water is filling up, that's describing that this is a positive value. Question A. At the instant when the depth is 5, so when my depth is 5, what is the rate of change? So there's my four-letter word. What is the derivative of height? What is d h dt? Okay, now depth, of course, is height, so I'm just going to say when h equals 5, what is the derivative of h? So here's the deal. We're always going to use this ratio to help us out, and these cones all involve this ratio that we've talked about. The ratio is radius to height. Now, I can't stress enough, you need to star this in your notebook. You use the original values for this. Okay, not what it wants to happen. You're using the original values. So we really should box this in. And we're going to say our radius over height equals the original radius is 4 when the height is 16. These two correspond together. I'm not using 5 whatsoever. Okay, that's at some instant in time. The original radius is 4, height is 16. So I'm going to say my radius is 4 with a height of 16, and then I'm going to reduce that to make my math easier and say that's 1/4. Now, I'm going to go one step further. I'm going to cross multiply and solve for both variables. I'm going to say 4r equals h, and h equals, r equals h over 4. Okay, because I don't know if I want the h equals or the r equals, so I'm going to write both of them down. Obviously, I just divided by 4 there. And let's box that in. That is the ratio we're going to use in this problem. So we do need to know our volume formula. And of course, volume of a cone, we'll have to memorize all these, is 1/3 pi r squared h. Now, we always want to check for constants. Okay, just like we did with the triangles. Is anything going to remain constant? Well, think about this. As you fill up your cone, okay, as the height gets bigger, so does the radius. Okay, so you can look there, the radius is that big when my height is that amount. If I fill it up even more, my radius just got bigger, so nothing is staying constant. So I cannot plug any numbers in. But what I can use is the ratio. Now, the next thing I have to determine is if I want all r's or all h's. And it's very simple. You just ask yourself, what do you want in the end? I am finding d h dt. That means I only want to see the letter h. So my goal is to rewrite my volume formula with only the letter h in it. And that's where the ratio comes in. I want to get rid of this r, so to do that, I'm just going to use the ratio I wrote for r and substitute in h over 4. Now because that was r squared, I need to say that's h over 4 squared, and then times the other h. Now, I just want you to notice we have not done any calculus. This is all simple algebra stuff you actually should have done in geometry. I'm going to continue to clean this up with zero calculus involved. 1/3 pi. If I square this, when you square a fraction, square the top and bottom, times h. So volume equals, I can do my 1/3 times my 1/16 to get 1 over 48 pi. And h squared times h is, of course, h cubed. Now that I have this nice simplified equation, I'm going to take its derivative with respect to time. So we'll bracket it in, and we'll put a nice d dt out front. Derive this function with respect to time. So variables don't match. The derivative of v is dv dt. Okay. Basically, there's only one variable in the problem, and it's h cubed. Do you know how to take the derivative of h cubed? Of course you do. It's like x cubed. And this is just one ugly coefficient, so that just stays there as 1 over 48 pi, and the derivative of h cubed is 3h squared, and then of course d h dt. Okay, again, this is just one ugly coefficient. This is the only calculus in the entire problem. Okay, now I'm just going to go back and substitute everything I know in. I believe they told us dv dt was 2 centimeters cubed. And I've got 1 over 48 pi, 3. They told us they want to know this problem specifically when my height or my depth is 5. So I'm going to put x squared is 25. I'll have to ignore our dog dropping things. dh dt. And then I'm just going to keep cleaning this up. Of course, this is going to be non-calculator, so clean it up nice and slowly. So I've got 1 over 48 pi. 3 times 25 is 75, dh dt. And again, I clean up a lot of steps just so it keeps my math neat. I can multiply these. That's, of course, over 1. So I've got 75 over 48 times my pi, dh dt. If you're ever uncertain where your pi goes, just remember it's pi over 1, so it goes on top. And if that helps, go ahead and stick it in there. And then to get dh dt by itself, I'm just going to multiply by this guy's reciprocal. So I'm going to flip that and say that's 48 over 75. If that's pi over 1, that is now 1 over pi. And I'm going to multiply that to both sides. Alright, and then again, I'm just multiplying my tops, multiplying my bottoms. So I get 96 over 75 pi. And I think that cleans up real nice. I would say both numbers are divisible by 3. So I get a 25 pi in my denominator. And on top, 32. Now, lastly, this guy just needs some units. So if I go back and think about what I was finding the rate of change of height. And the height was in centimeters per second. And there you have it. So this is how fast the height is changing, specifically when the height is 5 centimeters. Now, we've just answered question A in this problem, so I'm going to scratch that, and now we're going to attack question B. So it's the same shape. I'm going to redraw mine out and label it. So I'm going to pause it and do that. You can do the same or look at your previous one. So I have my given information listed again, and this question says, when water is poured in, find the instant when the radius is 3. So when the radius equals 3, what is the rate of change of the radius? So now I'm finding d r dt. So we're going to use that same ratio, radius over height. And remember, we're using the original. So the original radius is 4. The original height is 16. And we said that reduces to 1/4. And if I cross multiply, I got my 4r equals h, or if I divide that, r equals h over 4. All right, so we'll start with our formula. Volume equals 1/3 pi r squared h. Okay, we're going to have to memorize that like we said. Now this time ask yourself, do you want to see all r's or all h's? We already know there's nothing constant. As you put more water in, the radius gets bigger. So there's nothing you can substitute in first, no numbers you can substitute in. So look at what it's asking to find. It wants dr dt. That means I only want to see r's. So as I go through, if it doesn't have an r, I've got to replace it with something. So 1/3 pi r squared, and I don't want to see h, I need r. So I'm going to replace it with h is equal to 4r. And now I'm just going to clean it up. So I've got volume equals 1/3 times 4/1 is 4/3 pi r cubed. So again, I've done zero calculus up until this point. Now I will take its derivative, because it's in terms of r, with respect to time. So I get dv dt equals, remember this is just a constant, so keep your constant 4/3 pi, and the derivative is really just the power rule of r cubed. 3r squared, and then of course dr dt. That was the only calculus in the entire problem. Now we'll clean it up before we substitute in. I've got dv dt equals 4/3 times 3, of course, is just 4 pi r squared dr dt. And the question said, what is dr dt specifically when the radius is 3? So my dv dt was 2. My radius is 3, so this is r squared, so that's going to be a 9 dr dt. I've got 2 equals 36 pi dr dt. And lastly, when I solve, I get 2 over 36 pi, notice that's in the denominator, dr dt. And clearly that reduces to 1 over 18 pi. Now again, I need to slap some units on this puppy, and this was centimeters per second. All right, next question. Water is being withdrawn from a conical reservoir 3 feet in radius and 10 feet deep at a rate of 4 feet cubed per minute. So again, let's stop, draw the picture. Okay, so I've got a conical, there's my cone. Radius, 3 feet of radius. Okay, sometimes they'll give you the diameter, so make sure you read carefully. 3 feet of radius, and a 10-foot deep. Okay, now these are the original, keep that in mind. And it says it is being withdrawn at a rate of 4 feet cubed per minute. Now, notice the units. That feet cubed is telling me that's dv dt. And because it's being withdrawn, I'm going to say that's negative 4 feet cubed per minute. Here's the first question. How fast, so that's the rate, is the surface falling when the depth of the water is 6 feet? So what are they asking? How fast is the surface falling? They want to know how fast the what is changing. If this surface is falling, I'm talking about the change in height. So the question is, what is dh dt? How fast? What is the rate it's falling? Specifically when the water is 6 feet deep or has a height of 6 feet. All right, so we've got to set up our ratio. All cones have this radius over height ratio. Now remember, the key thing we marked in our notebook was we'll use the original. What original numbers are my radius and height? Well, that's 3 over 10. So then I'll just do a quick cross multiply, and I get 10r equals 3h. And I'm going to solve that equation 2 ways, because I don't know if I want the r or the h yet. The radius is 3h over 10, or I could go the other way and say the height equals 10r over 3. All right, and I'm going to have to figure out which one of those I want. So I know my volume is 1/3 pi r squared h. Do we have any constants? Well, again, as this volume changes, as the height changes, so does the radius, so nothing is constant. Now, I'm looking for dh dt. That means I only want to see the letter h. So I'm going to go through, and if it's not an h, I'm going to replace it. 1/3 pi, all right, I don't want radius, so I use my ratio, and I'm going to put in 3h over 10, squared of course, times h. Now it's just lots of cleanup. If you skip these steps, you're likely to make a million errors. This becomes pi, this becomes 9h squared over 100, h. Keep cleaning up. I'm going to say I get 9 pi over 300, h cubed. Now I think I can clean it up even further, so I'm going to say volume equals, they're both divisible by 3 pi over 100, h cubed. Wrap that bear up. We're going to take its derivative with respect to time now that it's cleaned up. So I get dv dt equals, remember this is just a constant, it's all a number. 3/10 and pi are all a number. So you're just bringing it along for the ride. 3 pi over 100, the only derivative you're taking is of h cubed. So 3h squared d h dt. And remember the question is what is dh dt? And we know that our volume was leaking out or getting smaller. So our volume was a -4. I've got my 3 pi over 100. I've got 3. Specifically, when the height was 6, that means this term is going to turn into 36 dh dt. Whew. All right, we're just going to keep cleaning her up. 3 times 3 is 9. And 36 times 9, might have to do a little scratch work off to the side. 9 times 6 is 54, carry my 5, that's 27. That's 32 over 100. My pi's on top. dh dt. And then, of course, I'm just going to multiply by the reciprocal to kill it. Remember, that's pi over 1, so I'm multiplying by 100 over 324 pi to both sides. And as I clean that up, those of course cancel, and I get dh dt equals, it's that times -4. So I'm going to say that's -400 over 324 pi. Now of course this can get reduced. I can easily divide by 4, so that gets me a -100 on top. 4 goes into 32 8 times. And into 4 once. So I get -100 over 81 pi equals my dh dt. And lastly, I'll slap some units on there. Oh, I already forgot what they were. If I go back, this was all in feet per minute. Our last problem for the night. Sand falling from a chute forms a conical pile. So let's stop there. I've got this chute, okay? And it's dropping out sand, and as the sand piles up, it's making the shape of a cone. Hopefully you can picture that. And now it describes whose height is. So to me, I read h equals. Height is equal to 4/3 the radius of the base. Okay, so I'm saying the height is 4/3 the radius. How fast, so they're asking for a rate, is the volume. They're asking for dv dt changing, specifically when the radius is 3 feet and is increasing, so the radius is increasing, that is dr dt, at a rate of 3 inches per minute. Okay, so again, I'm highlighting everything I know, I'm pulling it off to the side. Now there's a lot to pick up on here, and this is why we had to make sure we attack this last one. Right here, okay, this is the AP being nice to you. You may not see it, but they're taking out half of your work. Notice they didn't give you an initial or original height to radius ratio. They gave you this instead, so you don't have to do it on your own. They're telling you this is the ratio. The height is 4/3 times the radius. They gave you the ratio. So that's the first thing you have to catch. The second thing, and they put it in italics, they told us the base is 3 feet, and it's increasing at a rate of 3 inches per minute. 3 feet, 3 inches per minute. We've got a big problem there. We can't solve this problem if our units don't match. All right, so I need to convert everybody to the same thing. So I'm going to change this 3 inches per minute into feet per minute. That is my goal. Okay, and it's very simple. You write a basic ratio that you did back in 6th grade whenever you learned ratios. I'm going to say 3 inches per minute, per 1 minute, times what will get me feet per minute. Okay, I want feet per minute in the end, so I'm saying 3 inches per minute, that's this ratio that's given, 3 inches per minute, times what over what will get me feet per minute. Okay, so basically I need to get rid of inches, so I know I need inches on the bottom and I need feet on top. Would you agree with that? Then my inches cancel and I get feet per minute. So what's equivalent? Well, 1 foot is equal to 12 inches. So again, I just wrote a ratio, so I get in the end feet per minute. My inches cancel, and I get 3 feet over 12 minutes, also known as 1/4 feet per minute. Okay, so again, if I went too fast, pause it and go back. So I can now say my dr/dt is 1/4 feet per minute. All right, so let's set up our formula. We have volume equals 1/3 pi r squared h. Nothing is constant because as this pile gets bigger, so does the radius. So at this point, I have to ask myself, do I want all r's or all h's? Well, the question is, what is dv dt? So that doesn't give it away. But they give me dr dt. So they're telling me I only want to see the letter r. So volume equals 1/3 pi r squared. Okay, I can't have an h here. What can I put in place of h? Well, they gave you the ratio. Height is 4/3 r. So 4/3 r. Clean that up before we derive. Volume equals, I'm going to say 4/9 pi r cubed. Now I can bracket that in, and I'm taking the derivative with respect to time. So I get dv dt equals, remember this is just the coefficient in front of r cubed. So I'm going to keep my coefficient, 4/9 pi, and I'm really just taking 3r squared dr dt. Carefully plug everybody in. I'm looking for dv dt, that's the only thing I shouldn't know. 4/9 pi, 3. My radius was 3, so I'm going to say 3 squared is 9. And my dr dt we said is 1/4. So as I multiply again, I'm just going to do tops and bottoms. You don't actually necessarily have to multiply. Look for things to cancel. For example, this 9 on the bottom cancels with this 9 in the numerator. This 4 on the top cancels with this 4 in the denominator. So I basically get dv dt equals 3 pi. And I've put it in correct units, so that's feet cubed per minute. Why am I putting feet cubed? Did you catch that? I am describing to you volume. So make sure we have the correct units on there. Well, that does it for us tonight. I know these are long notes for the couple days here, but we're going to have to get over that part. Pause, rewind when you need to, and we'll see you tomorrow.